we have Laura Brewington, a research fellow at the East-West Center and the leader investigator of the Pacific Island Climate Health and Migration Project and an investigator for the Pacific Regional Integrated Science and Assessment Program. So she designs and conducts collaborative policy-oriented research using spatial analytical tools to support climate adaptation in Pacific Island. So her talk is like this, and then so welcome her for a great talk.
Thanks, Harry. I am maybe the newest adjunct faculty member with the WRRC, so this is my first seminar with you guys. It's great to be here. It's nice to see familiar faces. For those of you who don't know me, I'm Laura Brewington. I've been at the East-West Center just across the street, whichever way it is, for about 7 years, working in climate adaptation. I'm actually a geographer by training. My background is remote sensing and spatial analysis. And I previously worked in Galapagos on conservation and climate-related projects for many years before I came to Hawaii. It's a pleasure to be here. Happy Valentine's Day, which I thought I would add into my title slide here. As a matter of fact, right after this talk, I'm flying to Maui for vacation this weekend. So without further delay, today I'm going to be talking about some work that was actually part of the first project that I worked on when I moved to Hawaii back in 2013. This project took quite a long time to reach completion, but we finally published all of the results late last year. The title of the paper that we published is Simulating Land Cover Change Impacts on Groundwater Recharge under Selected Climate Projections on the Island of Maui. Sorry, I'm hopefully not going to screw up the slides with this fancy screen that I can touch and ruin it all. So the National Climate Assessment that came out in 2018, who's heard of it? 2 people in this room have heard of the National Climate Assessment? Okay, 2.5. Well, according to the National Climate Assessment's Hawaii and Pacific Islands chapter, which some of the people who raised their hands in this room were involved in helping author the draft, the climate impacts that we're seeing in Hawaii also have impacts on groundwater recharge in the islands. And what I'm showing here is a summary of both climate impacts and land cover impacts on groundwater recharge. And this is not just applicable here in Hawaii, it's applicable in a lot of coastal situations and islands in general, especially high islands like we see in the Pacific. So starting with the column on the left, we're seeing air temperatures rising. I'll go into that a bit more in the next slide. Changing patterns of rainfall here in the state of Hawaii and elsewhere in the Pacific. Rising sea levels, I'm sure that you're all aware. Decreasing base flow in streams, which impacts groundwater recharge, groundwater supplies, and changes in extreme events, which also alter land cover through erosion and other modifications to the land surface. On the right, in islands, we see a lot of coastal development that's causing land cover to impact the groundwater supplies and recharge due to increased impervious surface cover in coastal areas. With that increased urban development and population growth, we also see higher pumping rates for groundwater, reducing groundwater supplies. At the higher elevations where groundwater recharge typically takes place, we're seeing changes in the forest makeup. In some cases, loss of forest cover. In some cases, shifts from native forest to alien forest. And lastly, the land cover impact that I want to touch on is changing agricultural patterns, which you'll see quite clearly demonstrated in this study as we look at sugarcane on Maui and the absence of sugarcane, the impacts on groundwater recharge there. So just to quickly cover 2 of the top climate impacts on groundwater recharge. I'm not saying these are the most important, but these have been quite well observed and very substantial in Hawaii over the last 20 to 30 years. We're seeing rising air temperatures. So what you see here is the average annual change in air temperature in Hawaii since 1910, since record keeping began. And in particular, since the 1970s, what you see is a lot of bars in the red. That means higher than usual temperatures. Average temperatures have increased by just a little under 1 degree Fahrenheit per year over the last 100 years. And we're seeing, not per year, sorry, but just over the last 100 years, they've increased by about 1 degree. And 2015, 2016, and 2019 were the hottest years in record here in Hawaii. Some of the higher elevation areas in Hawaii have experienced much more rapid warming, which is really alarming and has impacts for forest makeup, but also evapotranspiration rates, which impacts groundwater recharge. And so again, here at the bottom, the impacts of increasing air temperatures include increased evaporation, increased demand for water and a reduced water supply, and habitat loss for species at the higher elevations. In combination with rising air temperatures, the rainfall patterns in the state are also changing. I've highlighted Maui rainfall anomalies here in the red box, but what you see statewide is a browning trend over the last, let's see, which is this? This is decadal change. So percent of change in rainfall by decade, and the areas in hashes are areas where that change has been statistically significant. What we're actually seeing statewide is a drying trend with more consecutive dry days, but also more consecutive wet days. So when it rains a lot, and it rains for a long time, which leads to runoff and erosion, and not always leads to groundwater recharge. These extreme rainfall events have been occurring, and I think most notably, we all remember what happened in Hawai in April of 2018. The same thing followed on Oahu. We had a huge amount of rain in a very short amount of time. But in Maui, there's been very pronounced drying on Maui in the last 30 years, and especially in that area that's in black hash marks, particularly since 2008. So what does this mean for groundwater recharge? It means there's reduced water supplies. It also adds to groundwater demand. Agricultural losses. Ranches have had to sell off many of their heads of cattle, for example. And in windward Haleakala there, on the windward side of Maui, of East Maui, and in the East Maui Mountains, we've seen extreme, statistically significant drying. So the motivation for this study actually began in 2012, when the Hawaii State Legislature signed the Climate Change Adaptation Priority Guidelines into law. This effectively mandated all state and county agencies to incorporate climate change impacts into their planning processes. So what I've shown in the schematic on the left is a breakdown of the state and county water planning architecture. So at the top left are plans that are related to water quality. So the water quality plan for the statewide water resource protection plan, for example. On the right, we're looking at needs or supplies. So the agricultural water use and development plan and the state water projects plan. And then kind of at the bottom, we break it down by county. And each county has its own county water use and development plan. And in 2012 and 2013, the County of Maui, Department of Water, was beginning to update their water use and development plan. And their goals were, as they have been in the past, number 1 and 2, to protect and manage the use of water resources over approximately a 2-decade, 20-year period, and to allocate water responsibly according to projected growth and demand. But the third mandate that's now included since 2012 is to incorporate climate change impacts. And so our team over at the East West Center and the U.S. Geological Survey were approached to discuss this issue and how to best incorporate climate change into the plan. So the goals of the study, because groundwater is such an important resource for all of the islands in the state, including Maui, is to quantify groundwater recharge on Maui under different climate conditions and under different land cover conditions. So specifically, we're asking a how, what, and where type suite of questions for this study. First of all, how can we use climate projections to inform planning on Maui? And I mean planning for urban development, planning for agriculture, planning for conservation, a holistic way of looking at Maui's impacts due to climate change. What are the impacts of climate change and land cover change? What are the impacts combined on groundwater recharge? How does climate change impact recharge on its own? And then how does land cover ameliorate or worsen the impacts of climate change? And where should the adaptation efforts for things like drought or extreme events and flooding be concentrated? If we really have limited resources and are looking toward an uncertain future, what are the areas where groundwater recharge, for example, could be impacted the most by climate change and land use? So as I mentioned, the study was sort of incepted in 2012. We began having interviews with stakeholders on Maui and here on Oahu with the Commission on Water Resources Management. By 2014, we had used those interviews to generate plausible scenarios, and I'll go into that in more detail in the next slide. But this is effectively a menu of land management options for the future. So sort of a suite of narratives about land use on Maui, what it could look like in the future under an uncertain climate future. Then we selected the climate projections that we wanted to use to sort of bracket the future climate between a very dry future climate and a very wet future climate for Maui. Then we began to build the current and future land cover maps, the GIS layers that were going to be used as inputs into this modeling exercise The USGS had developed a water budget model that we used to run under these current and future climate projections, as well as the current and future land cover scenarios. And lastly, at this point now, the results of the groundwater for Maui island-wide have been published, but we're now looking at very localized areas, and we're trying to identify hotspots, places where groundwater recharge maybe changes the most under different climate change projections and land cover uses, and zero in on what are the very real impacts of this. For example, what is the water valued? Kind of moving from a raw numbers groundwater recharge model to an economic valuation. So I'll just, again, quickly overview the water budget modeling framework. This was developed by USGS, green circle in the center. That model receives multiple inputs, which are sort of arrayed in a constellation on the outside, including the UH Geography Department rainfall and evapotranspiration atlases. Hello, Abby, in the back. Hello, wave to everyone. If you need rainfall and evapotranspiration information, she's your girl. That's one of the inputs for the water budget model. We also use two separate climate projections, which I'll go into in a bit more detail in a moment. Current and future land cover maps for the entire island of Maui. Soil characteristics were input into this model, and vegetation characteristics for each of the land cover types, which were very complicated to develop and came from multiple different sources. So all of these were plugged into the water budget model. The model was run many times, and the outputs are the recharge projections. And I'll go into more detail in just a moment. I want to, in case anyone here actually is a hydrologist, I'm not a hydrologist, so it took me a while to really grasp how massive this water budget model concept was. So the USGS has actually developed this model for use in Pacific Island settings, and the same model has been used here in Hawaii, but it's also in Guam and American Samoa. The required input data sets that I showed in the previous slide include rainfall, evapotranspiration, and direct runoff. Those data sets get modified in order to estimate the impacts of climate change. The other inputs are the land cover inputs. Those data sets get modified to emphasize the impacts of land cover change. And then lastly, soil properties. And the publications that I've listed below are a series of the USGS reports that the USGS has put out over the last several years for the island of Maui. And they kind of have progressively expanded and refined this model. So these two maps actually show the rainfall, the mean annual rainfall anomalies expressed as a fraction of the current day mean. And the map on the left shows what we've used as the dry climate projection for the island of Maui. The dry climate projection was never intended to be a dry climate projection, but it was the results of a statistical downscaling approach that took the RCP 8.5 projection for Maui, or for the globe, effectively, and downscaled it to the island of Maui at a very fine scale, spatial scale. It projected quite a bit of future drying on the island, as you can see in the red and the brown colors on the map on the left. Some significant drying in particular is projected to occur in leeward Maui and central Maui. The map on the right, on the other hand, looks significantly less red and more blue. This was the result of what we've called the wet climate projection for Maui, and it was the result of a dynamical approach to downscaling here at the IPRC. This was from the CMIP3 A1B scenario, so it's not quite the same generation of climate scenarios as the projection on the left, but it was what was available at the time when we were selecting the climate projections for this project. And we chose these two precisely because they diverge. It would have been nice to see all of our downscaled climate products for the state agree everywhere, but they don't. And stakeholders on Maui were particularly interested in seeing a range of possible future climate impacts. And so we chose these two extremes for comparison's sake. And Chip's going to ask me this later, which one is right, and I don't know. But that's why you have to plan for uncertainty. So anyway, the summary of the slide is that the left image shows the dry climate projection with a significant amount of drying, especially in leeward Maui. On the right, we see wet areas of Maui that already received a lot of rainfall, for example, in the West Maui Mountains, higher elevations, and eastern and southern East Maui seeing increases in rainfall. And this just highlights the differences between the two projections. So overall, the dry climate projection shows a 13% decrease in mean annual rainfall compared to today. And On the right, the wet climate projection predicts a 10% increase. So it's almost exactly the opposite on the island-wide scale. The areas where they agree are actually just still shown. Areas where they disagree are whited out. So again, they both agree that there will be some drying in central and leeward Maui and some wetting in northeastern Maui. But here we see where they disagree. And one of the key points of where they disagree is in the West Maui Mountains. We have drying under the dry projection and wetting under the wet climate projection. And the same patterns are seen also at the higher elevations of windward Haleakala and along the southern coast of eastern Maui. The land cover inputs included a current land cover map, which is shown here. And those of you who are close to the small screens will probably be much better able to read the land coverage heights than you can on this slide. But effectively what you see is a current map of what land cover today looks like on Maui. This actually began with a 2010 map of Maui that the USGS modified to include additional agricultural classes like sugarcane, pineapple, coffee, macadamia nut, things that didn't exist in the classification that they started with, which was land fire data set. So they added all these classes. They actually had to combine other classes because they didn't have the correct parameters for the water budget model for that vegetation cover, so they removed other classes. And then around 2016, Hawaii Commercial and Sugar decided to close sugar operations on Maui, which meant that the entire area of central Maui that had previously been classified as sugarcane needed to be reclassified. And so the map was updated to represent 2017-ish conditions with a large portion of central Maui now being classified as fallow. To develop the future land cover maps for Maui, and this is where I actually stepped into the project around this time in 2013, 2014, we worked with stakeholders to start to generate these narratives about the future. And when I say narratives about the future, we asked people to think in terms of these axes of extremes. So when you think about land cover and forest, for example, what are the extreme future possibilities for forest cover on Maui? So on one side, stakeholders would say, totally overrun by alien vegetation, no new protected areas, no active restoration or outplanting of native species. And on the other side, stakeholders were saying, well, what if we have a huge amount of financial investment in forest protection and fencing for ungulates? And so we did this for forest cover, we did this for development, for urban build out and densification, and we did this for agriculture and ranching. And finally, for stream flows. So we just asked stakeholders through these iterative meetings to imagine the management extremes for whatever lands that they manage, and then to come up with a menu of options of what they would potentially like to see in the future, or what they would be afraid of seeing in the future. And the results of all of these conversations were the four maps that you see here. They use the same land cover classification as the current land cover map, but they're quite different, and you'll see more of the differences in future slides. But here I just want to highlight each future scenario very quickly. So starting at the top left is what we couldn't come up with catchy names for these. No one could agree on the names that we came up with. So we're just calling it Future 1. But this future is what a lot of people would have called the green sustainable future, where there's a lot of investment for forest conservation, in particular in the upper watersheds at the very highest elevations. I used a lot of GIS data sets that existed for the state of Hawaii and for the watershed partnerships and their management plans to literally fill in areas that should be or hopefully will be restored under a future where there's very high investment in forest conservation. At the same time, this scenario, stakeholders wanted to see quite low urban expansion. And so we used some of the data sets from the Maui Department of Planning to narrow down some of the highest, the most likely build out projects that are already planned, and then cap development on Maui at that point. So a fairly limited amount of urban expansion is in this scenario. And we also wanted to emphasize the development of local agriculture. And so that involved placing quite a bit of diversified agriculture, which is in the red color, in the place where sugarcane once was, in lands that were formerly fallow. So that summarizes the future 1. The future number 2 on the top right represents a more business as usual kind of current land cover trajectory. This is the goal of this was to say, if we don't really do anything, we just keep the status quo, what will the impacts on groundwater be in the future? So here you see the central Maui Isthmus remains fallow, and there's quite a bit of expansion of native forest, alien forest, which is in the purple colors. So if you compare the top left map to the top right, you actually see a lot more purple at the higher elevations of West Maui and then along the coast in southeastern Maui as well. And so that's without more active investments in forest conservation. Down to the bottom left, this was a lot of people's worst case scenarios. This is where we hypothesize that there is no active forest management, and alien forest in the purple colors actually really expands at the highest elevations of West Maui. So that's envisioning a future where there's no ungulate fencing that's added. We lose a lot of the native forest cover, and where urban build out is quite extensive. So this would be building out to the very limits of Maui's existing urban zone categories. So what you'll see in that bottom left map, you'll see in the middle there is a red area. And the final thing that we wanted to add in this scenario was the production of biofuel as a potential energy source. So the goal was to be more sustainable in terms of energy production, but less sustainable in terms of conservation land cover. And finally, on the right, on the bottom, was our fourth future land cover. And this emerged, we had actually only created the first three through these iterative meetings with stakeholders. And then in our final meeting, we showed the first three maps. And several of the stakeholders said, well, why can't we have a future where there's a lot of forest conservation, but there's also a lot of urban development? You know, is that possible? Which, of course, we're not predicting the future. So anyway, it's possible. So we decided, after that meeting, that we should create a fourth land cover map that shows a very high level of watershed conservation effort, but also very extreme urban expansion. So again, it's sort of a combination of the top left and the bottom left, where you see quite a bit of forest, native forest in dark green at the higher elevations of the mountains, but also quite a bit of the gray and the dark gray colors along the coast, especially near the area of Kihei, which is highlighted as a blue arrow there on the bottom right. Have I lost you guys yet? Everyone okay? So I basically just gave you the basic components, the future climate projections, and the current and the future land cover maps that were used as inputs to this water budget model. This table just shows the number of model runs that we did in order to get a suite of outcomes that would show the impacts of just climate change if we don't change the land cover at all, and the impacts of just land cover change if we don't change the climate. So we did, in total, there were 11 water budget model runs, and I'm not going to show you all 11 outputs because that would take a long time, but if you want, you can read the paper, which I'll show a link for that at the end. So first I want to show the impacts of climate change. So these four maps actually are referred only to groundwater recharge under the current land cover, but under a future dry climate on the left and a future wet climate on the right. The top two maps look almost identical. On the left, under the dry climate projection, the main difference is that you see a lot more of the dark red. If you compare it to the map on the top right, you'll see that the areas that are sort of yellow and blue and green, they contract when you move over back to the left. So there's more recharge given under the wet climate projection, holding the land cover the same. But the recharge actually just sort of takes place in a lot of the same areas. So spatially, climate change doesn't have too much of an impact. On the bottom, however, you see a bit of a different story. So the bottom two maps actually show the projected change in mean annual groundwater recharge in millimeters under the dry climate projection and under the wet climate projection. So what's the difference here? Does this look a little bit like those rainfall maps that you saw a few slides ago, where the bottom left looks like around the West Maui Mountains, you're seeing a lot of drying. On the bottom right, it looks like it's getting wetter. The bottom left, you see a lot of red all the way around Haleakala, except for the very windward coast. On the right, you see contrasting quite a bit of wetting coming around that side. So what we noticed first of all is that the change in rainfall has a huge impact on groundwater recharge in the future. Now let's look at the impacts of changing the land cover. The two maps on the top just show land cover only in the areas where they changed according to the scenario. So rather than overwhelm you with all of the land cover classes for the entire island, I'm only showing the map on the left, the top left, which is 2017 current land cover, and the classes that changed when we created the future one land cover map, which is shown on the right. So on the top left, you see a lot of yellow. That's mostly grassland cover or fallow areas that were converted into Future 1 on the right as diversified agriculture there in the Central Isthmus, or as native forest here in the upper elevations of Haleakala as well as West Maui. So there's not too many different changes in the land cover, but what are the impacts of those changes on groundwater recharge? And if you look at the two maps on the bottom, you can see in the dry climate scenario, you see sort of a faint wetting signal in the areas that converted to native forest. Especially along the southern coast of Haleakala, but at the higher elevations. The black lines on all of these maps, and I'm sorry I didn't mention this previously, the black lines actually indicate the limits of the cloud zone. And so what we see on these bottom two maps, actually, you see the similar trends. You just see more wetting under the wet climate projection than you do under the dry. Is that above the cloud zone in areas where grassland, so again, look at the top left map where you see the yellow, and then look at the bottom, both bottom maps where you see blue within the cloud zone. That's where grassland was converted to forest. And most of the time that was grassland being converted to native forest, but it also occurred when grassland was converted to alien forest. So grassland conversions to any type of forest within the cloud zone actually resulted in higher recharge. The opposite was true below the cloud zone, where we saw grassland being converted to alien forest, which resulted in red on these two bottom maps, or decreases in recharge. So we thought that was a very interesting finding under this Future 1 scenario. The other things that I want to point out about this scenario is that Future 1 and also Future 4, which was sort of the best of all the cases, both of those scenarios incorporated a large amount of coastal taro production. And as many of you know, taro requires quite a bit of irrigation. And so in the areas where we added taro land cover, which are really hard to see because they're very small locations on these top maps, those areas experienced huge increases in recharge. So like the scale in the legend on the bottom actually shows the change in recharge of 32,000 milliliters per year. So that's like 30 meters, I think, yeah, 30 meters of additional recharge a year, which is a lot. And that's due to the impact of adding taro in these very small areas. And I'll get into that more when I talk about some of the localized changes in land cover. So I'm going to quickly go through Future 2 land cover results. These are the same type of maps as you saw on the previous page, but one thing you'll notice is that the changes, there's just less of a dramatic change because this was less of a big change type land cover scenario. So here, yes, you do see some of the yellow, the grassland being converted to forest. Most of the time in this scenario, it was converted to purple or alien forest. And that resulted, again, if you look at the bottom maps where there's purple on the top right, you see blue in some areas, but red below the cloud zone. So again, any type of grassland converting to forest above the cloud zone resulted in increased recharge, whereas below the cloud zone, if it was alien forest, it decreased recharge. For the third feature, this, remember, is the worst case scenario, you see a bit more red in these two bottom maps. The losses to recharge were more substantial in this scenario than they were anywhere else. Recharge did still increase when non-forest land cover was converted to any kind of forest above the cloud zone, as in the previous. Recharge also increased in central Maui in the isthmus, where we added biofuel for energy production. So that was an interesting impact. But recharge decreased when we lost native forest to alien forest, and that's especially noticeable in the West Maui Mountains above the cloud zone. You see red there where you didn't see in previous scenarios. And actually in this scenario, not even the golf courses were spared. They were mostly paved over for development, and so there were huge losses of recharge due to the loss of golf courses. And finally, our utopia scenario, where very high investments in conservation coexist with very high urban development. Again, we see more of a blue recharge increase overall across the island in the bottom maps, and once again, the same patterns of grassland being converted to forest, any kind of forest above the cloud zone results in increases in recharge. Most of the urban expansion resulted in modest increases in recharge. Only some types of urban expansion resulted in decreases to recharge. And recharge also decreased wherever grassland was converted to alien forest below the cloud zone. That's especially visible along the south and southeastern coast of Maui. So island-wide, recharge actually increased at least a tiny bit under all of the future land cover scenarios. And this is compared to the 2017 land cover and its projected groundwater recharge under the same dry and wet scenarios. Under the dry climate projection, we saw slightly less increases in recharge, circled in red, than we did under the wet climate projection on the right. And futures 1 and 4 had dramatically higher recharge than futures 2 and 3. And that, again, is due to the inclusion of taro primarily, but also due to the addition of diversified agriculture and biofuel production. In future 2, with status quo futures, with business as usual, recharge was actually slightly higher than irrigation rates, which is a bit unusual, but it was mostly because of the maintenance of this fallow area in central Maui. And in future 3, as I mentioned, you can't even see the bar for future 3 on the map on the left. Under the dry climate scenario, it increased by 0.3 million liters per day. So very, very small amounts under the dry climate scenario, and about 34 million liters per day under the wet climate projection. But what all this got us around to is thinking about what kinds of land cover change had the most impact on recharge. So we decided to look at 8 separate aquifer systems that had very different shifts in land cover across the island. And those 8 are shown here in the graph on the right. And then we looked at each of the water budget model components: irrigation, fog interception, evapotranspiration, and recharge across each of those aquifers. And we found that certain land cover changes impacted groundwater recharge in certain areas. So for example, we know that irrigation increases occurred due to the addition of taro in future 1 and future 4. And by the way, this graphic is just shown for future 1. So the future 1 land cover emphasizing high investments in conservation, additional coastal taro, very low urban development, and diversified agriculture in central Maui. So we saw this diversified agriculture signal leading to increased recharge in many of the aquifer systems here, particularly in the Ihau aquifer system, Kahului, Paia, and Haiku, kind of those 4 in the middle of the graph. In Kamaole and Nakula aquifer systems, we didn't see that type of increase, mostly because there was no coastal taro in those aquifer systems. They were primarily dominated by fog interception, which caused increases in 5 aquifer systems where there were conversions to forest, to any kind of forest above the cloud zone. So that increase in fog interception led to increase in groundwater recharge. Total evapotranspiration was due to higher irrigation rates and fog intercept, and that occurred in 7 of the 8 aquifer systems that you see here. And recharge increases ranged from anything from quite a little bit less than 1 million liters per day to about 70 million liters per day. So just looking at Ihau aquifer system for a closer up example of these changes in land cover and the impacts on recharge, I've highlighted here the taro, which is the blue arrow on the left, on the sort of upper right blue arrow. That bright green color is where coastal taro was added in that changing land cover scenario. And then the blue arrow on the left, in the map on the left, shows where native forest was added above the cloud zone. And where we see in the Ihau aquifers, a mean annual recharge increased by about 70 million liters per day under this future 1, even under the dry climate projections. That's a lot. That's huge. And that's like a massive amount of water every day. And that was due to increases in irrigation, massive increases in irrigation, thanks mostly to taro, but also the diversified agriculture in red that's sprinkled around the taro patches, as well as increased fog interception. And again, you can see the recharge impacts on the right. The dark blue are these enormous increases in recharge due to taro. The still darker blue colors, especially above the cloud zone, are thanks to the addition of native forests. In Nakula Aquifer System, this really highlights the impact of forest. And what we saw here in this aquifer system is that mean annual recharge increased by about 10 million liters per day under the dry climate projection in Future 1 land cover. And this was due to increased fog interception. So above the cloud zone, you see purple and green land cover, that's alien forest and native forest. On the right, you see that both of those types of forests caused increased recharge. But below the cloud zone, you see decreases in recharge where there's alien forest. So again, this highlights the transition between the cloud zone and the forest type. So the summary in terms of the impacts of climate change, my take-home messages at least from this, is that focusing on areas where the climate projections actually agreed for Maui, both climate projections showed a drying trend in central Maui as well as leeward Maui. The order of magnitude of that drying is different, but they do agree. And this has pretty strong implications, as you've seen, for agricultural development and groundwater resources. If, in fact, the climate for Maui is this dry in the future, water conservation efforts will absolutely be needed, in particular if future development is going to proceed along that leeward central Maui coastline. Where the climate projections disagreed, we're in some of the most high priority conservation areas of Maui. So in the West Maui Mountains, for example, we saw a drying trend, declining rainfall under the dry climate projection, and we saw quite a bit more rain and potential groundwater recharge under the wet climate projection. So this upper watershed planning will have to take place under these conditions of extreme uncertainty. Certain aquifer systems on the bottom on the right had very strong disagreement in recharge. So this map is actually shaded to show where aquifer system recharge increased under both climate projections, where it decreased under both climate projections, and where it did not agree at all. So the colors of red, from sort of medium shade of red to very dark red, show that both climate projections said that recharge was going to decrease in those aquifer systems. Where they are blue, both projections agreed that recharge would increase. Unfortunately, the majority of Maui's aquifer systems showed a disagreement. So either one, wet climate projection said that the recharge would increase, and the dry climate projection said that it would decrease. And that was the most significant in Oluwalu aquifers in the dark gray coloring here, and Nakula aquifers. In those two aquifer systems, for example, the changes to recharge ranged from a decrease of 41% in Oluwalu to an increase of 13%. So very, very staggering differences in many of Maui's aquifer systems. As far as the impacts of land cover change, and we're still kind of pulling these details out and thinking about them more, what's unmistakable is the impact of taro. Adding taro land cover to any of these maps resulted in huge increases of recharge due to the added irrigation. But there are some problems with this question. First of all, where would this water come from? That was not modeled in this study. So the source of the water for the water budget model is still missing, and that's something that the USGS is working to fix. In addition to that, the taro land cover recharge rate. So there were fixed parameters for each land cover type that went into the model. And the particular rate that was used for taro was assumed to be spatially and temporally the same across the entire island. And so that recharge rate needs to be refined and modeled. For diversified agriculture, which also resulted in increases to recharge, again, the question of irrigation comes to mind. I think many of us know that water that was used to irrigate sugarcane in central Maui came actually from eastbound. So these things have not been modeled for this study, and the complex interactions between land cover and water supply need to be considered, especially with respect to changing water demand. For forest cover, again, the Nakula aquifer system on the bottom right really illustrated the fact that changing types of forest resulted in increases to recharge most of the time due to added fog interception. So above the cloud zone, changing grassland to any kind of forest increased recharge, but recharge actually decreased below the cloud zone when grassland was converted to alien forest. Currently, either the USGS as well as Tom Jampaluka's lab are working on better models that look at these different species makeup. And I don't know if any of those results have actually been published yet, but there's a lot of concern over what species of tree, what species of forest cover could be the most conducive to increasing groundwater recharge as opposed to what might be the most extractive. And this highlights the need to protect critical habitats and protect multiple ecosystem services, so not just water when it comes to forest protection. So these are the two publications that are associated with the talk that I've given today. On the left is the USGS report that came out around, I think, October of last year. On the right is our publication that came out in the Journal of Remote Sensing in December, pretty recent. And both of those can be downloaded from our project page, which is the landing page is at the top, pacificreset.org. I'm happy to leave up this slide I'll put it back on the slide in just a second, but I want to also say thank you to Alan Mayer with the USGS Pacific Water Science Center and Victoria Keener, my co-author at the East West Center. And I love this photo from Hanaho's December of 2016 issue of sugarcane on Maui before it was gone. Thanks, everyone. Sorry for the slide.